Hello everyone, and welcome back to fullrmc's workshop. In this session, we will be doing a hands-on tutorial using the two available versions of fullrmc. The version that you can freely download and install on your machine, and I also provided you with fully packaged standalone compiled version of fullrmc for the three existing operating systems. macOS, it's compiled on Mac 10.16 for Ubuntu and for Windows 10. So what we will be doing here is we will be running an existing file almost line by line, where I will be explaining all the steps along the way, and then I will be also demoing fullrmc SaaS version that exists on the cloud. So when you download the folder, which I called here Atomic Nickel Titanium, you should find in the folder the experimental data. Finished.stc is not there. You need to download the version that you need, depending on the machine you have, and we will provide a link from where you can download those standalones. Run_remove, and I will explain why it has _remove, and then system.pdb. When you double click and run the standalone version of fullrmc, what this standalone file do, it will search for a file called run.py, something like that. And if that file exists, it will automatically execute it. If not, you will get prompted right away to the console, where it's a Python console with fullrmc installed in it, along with all its dependencies. So since I didn't want to run the console and execute run.py, I renamed it here so I can launch the console from the directory in here without it installing or running run.py. So now I'll rename it again, and then, because that's how you would be seeing it. So here you have fullrmc installed and everything. Normally, when you install fullrmc using pip, for example, you have to import it and import all the definitions and the implementations that you need. So first of all, I will import here operating system, OS, and system. I will import NumPy. I will be importing the engine from fullrmc. And here we'll be using a pair distribution constraint and a distance constraint. I'm importing those as well. Those are the definitions that I will be needing to create fullrmc's engine and run it. Second, I'm creating variables just so I'm not redundant. And then those variables will have the file, the GOVAR file, which is the experimental file, the initial atomic system, and the engine path where I want the engine to be saved on disk. Fresh start equal false, that's a flag. Typically when I do my fullrmc run files, I make sure that if the engine is created, that I don't recreate it again. So I don't delete it and recreate it again. I just want to load the state and continue from there. So I create a flag called fresh start equal false. And fullrmc will check if this flag equal true, it will always recreate the engine. If this flag equal false and the engine exists on disk, it will load it instead. So let's do this line by line. So engine equal engine here. So I'm initiating an engine with path equal none. Then what's going to happen next? Fullrmc will check whether this engine exists. So this engine does not exist, as you can see in here. So let me execute that. And here, this on line 27, what's happening is, if the engine doesn't exist, or if fresh start equal true, fullrmc will always recreate the engine. It will delete what you have on disk and recreate it. But currently, we don't have an engine, so we're safe anyway. Let me do that. And let's see what's going to happen next. So now, if you read all what happened, the engine is created, setting fresh start equal true, but it doesn't matter. The structure is set to system.pdb in here. And then we created the pair distribution constraint. We created the atomic distance or which is the van der Waals constraint, and we added both constraints to the engine. What's left to do is to save the engine on disk. Let's do that. And notice what's going to happen. The engine is saved on disk. It's a directory. It's a repository. So when we expand that, you see all the files, and you see another directory in it, which is the currently used frame. So let me do that. Engine.used frame. It's frame 0, and that's frame 0. Those are all the files in frame 0. Those are the constraints that we just added. Those are the files of the constraints. It's a repository. Keep that in mind. It's a folder. Never touch this folder. Never remove files. Never attempt to update files manually. The only thing that needs to interact with this folder is fullrmc's runtime. If you touch it, you might break it. So next, what we want to do for the sake of this tutorial, the goal here, which I didn't mention yet, is to test multiple loss functions for that system and see how those loss functions behave during runtime, and how the choice of a loss function is very important to getting to a solution. And also, we will be using the loss functions with and without the corrections that fullrmc allows you to put your system. And the corrections here that I'm talking about is Qmax correction, which is also known as QDAM, the thermal vibration corrections, and the experimental resolution corrections. So we'll do that step by step. First, let me create another frame. And that's something neat about fullrmc. You can do those experiments in different frames, so you do not delete what you've already done before. And you can always come back and forth to certain hypotheses you're testing. So let me duplicate frame 0 and call it absolute error frame. Let's see what's going to happen. So I'm creating another frame here, you see it here, and it's a pure copy of frame 0. I know frame 0, we didn't run it yet, so it's going to be an empty copy, nothing there, but that's what we're doing. And here, let's do the same for 3 different frames, squared error. So I'm calling those frames according to the loss function we're going to be using there. And then absolute error with corrections and squared error with corrections. Let me create those frames as well. And you see how those frames are created for you here in fullrmc's repository. All right. So what I'm going to do now is start running the engine. Engine.use frame. You see we're currently using frame 0. I want to use frame absolute error. And now the used frame is absolute error. I would like to set the loss function. And if you don't know what the loss function is, probably it's not in the scope of this tutorial to explain what the loss function is. But technically, it's the way fullrmc computes the error between the model and the experimental data. So here we're using absolute error. We have in fullrmc's YouTube channel a short clip about the loss functions, and one of the loss functions that do not exist on the free version here that you have in front of you is the smart loss function that will continuously adapt itself along the way. So once you set it, it will know how to steer the simulation by itself using machine learning implementations. So let me set the loss function in here for absolute error. And then next, what's left next is to run the engine. But here I'm not going to run it for 1,000,000 steps. I will run it for maybe 1,000 steps really quickly, or 500 steps, and then save frequency equal 500. So to save the engine at the end, and then let me run that. The engine will be started, and now 500 steps are done. Let me do the same now for the other frame. So before I do that, let me plot the constraint here, constraints. So here you have 2 constraints, pair distribution constraint and the distance constraint. So I need the pair distribution constraint, 0.plot. And this is the current state. It's ugly, We only ran 500 steps. Nothing is minimized yet. We are still in the fully crystalline structure. We didn't relax the structure to get it to where it needs to be and to produce those bumps that are due to the shape memory alloy phase transition. At any time in this implementation, you can type info, and that will give you some help. It explains to you what you have available for you. One of the neat functions, which is clear screen, so you can clear the screen and start fresh. So currently the used frame is this guy, absolute error. I want to go and use another frame. And I will be setting another loss function. So now, remember, we were in this directory here. Now we are on that one, squared. I can always go back to this one and retrieve the state of the engine in this directory. So what I want to do now is run it again for 500 steps. Done. There is no need to visualize it. 500 steps is nearly enough to do anything. When you run this by yourself, you will always be watching this recording here, and you can listen to me again and listen to the explanation of what's happening. In this file, we'll be running fullrmc for 1,000,000 steps. Maybe you need to also run it more. That's not big of a deal because it will run fast. But also, I will show you at the end what 1,000,000 steps looks like, and we will explain the difference between the loss functions and what you should be doing when you're doing your science. So now let me use another frame here. Frame absolute error with corrections. I will set the loss function to absolute error AE. Now there are no corrections that are created for the paired distribution constraint. I need to do those corrections. The first correction I want to let fullrmc do, which is the thermal vibration correction, and I'm providing the parameters here. You can look to the documentation to see what those parameters are. It's fairly well documented. For Qmax or Qdamp, we're going to 25 reciprocal angstrom, and for the resolution correction as well. And then we will be running the engine for 500 steps. Let me do that just to show you that it's going to run. And then let me do this. Now we're shifting frames from absolute error correction frame to squared error corrections, setting the loss, setting the corrections, and then running the frame again. Remember, 500 steps is not enough. I'm just running the engine in front of you, just for the sake of the demo. You need to run it for much longer than that. At the end, when this is done, everything is being saved for you. Everything is saved in this repository. So currently we are in this engine, and look at the files in here. For example, this is updated 938, this is updated 932. So you see the difference. That's when this frame is created, and it's been updated now because we just ran the engine. So everything is saved. You don't need to worry about it. You never need to do this. You can always do that, but you never need to do it. fullrmc saved itself, updated its file, it's a repository. At any point in time, if you need to take this model to the cloud, you can execute this function, export snapshot, and you can take that file, and this file will be imported in the cloud. And you can do this the other way around. You can download the snapshot from the cloud and import it in your machine and run the engine on your machine. You can always go back and forth between all of that. All right. So let's get to this engine here, which is finished.stc. Previously, before this session here, I ran this file for 1,000,000 steps, and that's the final result. So let me load that now. So I'll do engine equal fullrmc.engine engine.load, and here I need to load this engine, which is finished.stc. Now the engine is loaded, so I am in this engine, not that one. And all what I want to do now is to download a snapshot to show you what a snapshot is. That's a snapshot. Let me double click here and show it to you. This is a snapshot file. This file you would be using to go between the web version and the local version of your machine. Now what I want to do is to plot the final results of the paired distribution constraint. Those are the plot functions here. I'm plotting frame absolute error, squared error, absolute error constraint, and squared error constraints. All of that is done. So that's squared error constraint. That's the final result after 1 million step. That's the final result for absolute error after 1 million step. That's squared errors after 1 million step. And that's absolute error after 1 million step. There is a huge difference between all of that. This is absolute error. Let me stress the difference between absolute error and squared error. You do not need to worry much about the value of the standard error. The value is relative. So 700 can be as good as 45. What you need to look at is the final result. So there's a huge difference here. Both engines ran for 800 steps. This engine here, this frame at least, absolute error frame, it was very slow. Not slow in terms of computation. It wasn't enough to bring the system fast enough to a solution. And actually the engine is stuck insert in a local minimum here. So you will not be able to take it out of there. You need to do other tricks like loss function warping that's also available on the cloud and other stuff like that. It's always wise to shuffle between loss functions to see which loss function will bring your system to a solution that you like. So here, absolute error is not a good loss function for this system. For other systems, it might be. Squared error, it is a better error. It brought the system from a pure crystal to something that looks like this, which is neat. So to get to the long-range ordering here, what is left to do is to train the system more, run the experiment more. And actually what one needs to do is to implement corrections, because there should be some widening put on the partials, and this widening is due to thermal vibrations and stuff like that. And there's also the resolution correction that needs to be implemented. So here we didn't implement any of this. We let the model figure that out by stretching the atoms longer in the space. It's probably not a bad fit, but it's not an ideal solution. All right. Now let's look at here when we implemented the corrections. The absolute error with corrections worked. It worked much better. Now, it needs more than 1 million steps, just to be clear, because when you look here, let me zoom in, this error here, this bump, it needs to be brought to the peak. The engine will do that. It needs more time because it's a different loss function. And again, this loss function is not ideal for this system. For another system, it might be. So 1 million step for squared error with corrections, and that's what you get. You get a beautiful fit. It probably needs a little bit more to fit the long range order, but that's a beautiful fit. That's almost ideal. So what you need also to look at is the scale factor. One of the main reasons you know that this system is far from being a solution is that we are hitting the limit of the scale factor. In here, the scale factor in the paired distribution constraint by default is set between 0.8 and 1.2. So you see here, the system is trying too hard to bring the intensity to where it should be. we are at a scale factor of 1.2. In here, we are at scale factor of 0.8 because fullrmc is trying to damp the long-range order to minimize the loss. And this is normal in the beginning stage of the foot to hit the maximum, but it's also gonna drop back and find itself somewhere in where it should be. For example, here the scale factor for this frame is 1.056. It's around 1. It's not random. We scale the experimental data to fit to that system. It should be around 1. In other systems, it can be as small as 0.02. If you have a purely crystalline system, you need to scale it down. So it doesn't need to be always around 1. Just to state an example, also here, for example, squared error is 1.15. And the reason being is because the long-range order is far from being done. You still need that, and the system is trying to accommodate for that. And also for here, for example, you'll have lack of intensity. This increase in the scale, try to bring the intensity to where it should be. Also here, you see, we're far from being done. We still have some error. We didn't fit the bump here. If we want to compare it to this, it's actually much better here because we have this correction. So I guess enough with that. Let me show you the web version. You can always run this whenever you need to. You have those files, you need to run them, you need to learn fullrmc, and I will always be here to help anytime you need me to. So going to the web version. This is the web version of fullrmc. Currently, I'm running it on my local machine, but this is going to be installed on AWS. So you would have your own machine and you would run it there. You would log in. I will call it here tutorial at fullrmc.com. Let me use 10 cores. And then let me log in. So here I have another machine that is running. So I don't have enough cores. I logged out from the other session and I have enough cores because the machine has a certain number of cores and CPUs. If it has, my machine here has 16 CPUs, I cannot use more than 16. So I had another session running on a different window that I'm hiding from the screen that was already using 10 CPUs, and I didn't have enough left to use here. So now I occupied 10 CPUs on that machine, and I'm logged in. That's my email, that's my name, I have my role, and when I logged in. Let me go to the engine tab. If I want to create an engine, I can create it here. Let me say test. If I want to upload a snapshot, that's what I can upload it from. All right. Let me do that, and then I'll create the engine. The engine is being created from the snapshot. Give it a couple of seconds. When it's done, the engine is created. Now I can find it in here, test. I can load it. I can visualize it. That's the current state of the engine. This is for frame squared error correction. This is squared error. This is absolute error. All right. So let me go back to engine. I don't want this engine anymore because I know I don't want it. What I want to do here is I want to create a tutorial from the web interface. And in that tutorial, I want to create the tutorial, which is nanoparticle size distribution, to demonstrate the mesoscopic computation for you. So let me create this tutorial. And what will happen here, when you create a tutorial, it will create an engine for you with everything set up for you to run it. And then you would learn from there. And there are extensive videos online to show you how to use the web version of fullrmc. So that's, okay, let me load the engine first. I'm using the tutorial one here. This is a nanoparticle. I have a multi-frame here of 9 nanoparticles. This is subframe 0, subframe 1, to show you that that's a distribution of nanoparticle sizes. I have many nanoparticles, and I want to figure out the distribution of those sizes in solution. All right, and that's a mixture of 10 models. And what will fullrmc do in the mesoscopic simulation run, it will run all of those structures together using the mesoscopic assumptions. I'm not going to explain that here, it's beyond the scope. And in the mesoscopic assumptions, fullrmc will fit all of those nanoparticles together, and then it will figure out a distribution of those nanoparticles that fit best the system that you have at hand. So here you can always create frames, similar ways. You can set the loss functions. Everything is using the graphic interface. There is no code here. There's nothing. You use only the graphic interface. You can visualize everything. You can set the selector, for example. You need to know what selector is. You can specify the groups, and you have many ways to do that. You can create the move generators. You will be adding the constraints, adjusting the parameters of those constraints, and also plotting the constraints when needed. So that's an initial plot in here. You know, that's going to take some time. All right, those are the 10 subframes. The engine is at the default state, never ran, nothing. So when you want to run the engine, currently I'm using a multi-frame. So I have the default frame 0 and all of those subframes for frame size distribution. And here you have 4 different types of run. You have the single, if you have a single frame. You have statistical, when you have a multi-frame where the metastructure is statistical, which is the case currently. You have the mesoscopic, and you have the nanoscopic. So let me show you what the difference is. When you go to frame, multi-frame metastructure, selecting size distribution. Currently, size distribution is a statistical multi-frame. A statistical means every subframe is completely separate. It's fitting the experimental data separately. The only reason why you want to do that is to minimize the whole multi-frame and every and each subframe in that multi-frame. And then you run it long enough using, for example, different fitting methods, using different loss functions. So you are leveraging the cluster to run all of those subframes separately. If I want to set a mesoscopic, so let me set it, and the reference frame, let's not go there. Let me open a new tab. Now, mesoscopic is activated for me because I am running in, because I set this subframe as mesoscopic. Let me go here and set a nanoscopic. And a nanoscopic is all of those subframes will create a single structure that you can visualize in front of you. The difference between nanoscopic and mesoscopic is nanoscopic, you have interaction between the subframes, and it's coarse-grained enabled. So you can create coarse graining also between the subframes. In mesoscopic, you are in the assumption of extreme dilution. So there is no cross-correlation between the subframes. So it's a mixture model. It's similar to mixture model with different things. So let me create it here as nanoscopic. And I don't know how, as I told you in the nanoscopic assumption, the subframes will have long-range ordering. So the position of those subframes is important. So let me randomize them in space. Before I do that, let me come here and show you all what it is. So now all the nanoparticles are sitting on top of each other. If I run that, it's going to be a disaster. Let me come here. Let me randomize it. All right. And then let me reload that. Okay, this is the structure now that we are fitting. 10 nanoparticles with inter-subframes correlation distances. And it's coarse-grained already. So it's a hybrid between atoms and coarse-grained. Atom-grained and coarse-grained. Atom-grained in the subframes, coarse-grained across subframes. You can reset that if you want to. Let me randomize it again. All right, let me reload. And that's a different randomization. So at any time now, if I go to run, nanoscopic is activated because If I try to run statistical or mesoscopic, it will tell me I cannot. Let me try that for you. It will tell me I'm able to do that because it's a nanoscopic structure. So normally when I want to run the mesoscopic or the nanoscopic, I set it first to statistical, all right? And then I run it as statistical for a certain number of steps. And in the statistical assumption, what is happening actually, I'm running the system in parallel using the cluster, using soft grid. And then when I do that, each and every subframe will attempt to fit the structure separately. So let me get here and show you what that is. Let me do the plot here. So here we're plotting 10 subframes at the same time. Give it some time. All right, see where we are now? Each and every subframe is trying to fit the structure separately. So what I want to do is to show you an advanced state. So let me stop that. Let me go to engine. And I want to load another engine where I've already done the computation. And this engine is a mesoscopic engine for the same structure. I ran it first in statistical. So size distribution subframe is statistical. I duplicated this subframe, this multi-frame, to mesoscopic, and I ran the mesoscopic. Let me show you. So that's the mesoscopic. All right. And it's not done yet. It still needs to run for, I don't know how many thousand steps. But that's the distribution of nanoparticles in that system. And the ratio is shifting. It's still shifting. We are far from being done, but the ratio is shifting. And the goal is to end up having a certain bell-shaped like distribution, which you will get at the end if you keep running it long enough. So now I am plotting mesoscopic. Let me plot size distribution, which is statistical. Oops, I cannot do that because I cannot plot mesoscopic ratio for a non-mesoscopic structure. So this is a statistical run. This is the first run I ran as a statistical before resetting the structure to mesoscopic and running it again. And this is the state of each and every subframe. All right, see that? So for example, the nanoparticle in subframe 9 is a very small nanoparticle. There's barely any correlation at long-range orders. So you have that now running. All right, I will stop here. I think that gave you a fast tour about fullrmc, on how you can run it on your machine, how you can go between machines from yours to the web-based implementation, how important it is to set the loss function. We didn't speak about a lot of other stuff. We barely scratched the surface. We didn't speak about what a selector does and how you can set different selection modes and how you can recur and explore the three-dimensional states differently and the hyperspace of the loss function. We did not talk about how you can reset the loss functions, how you can change the aggregations in the loss function and what the aggregation means, how you can reset warping to allow the system to always go out of local minima and always advance, how you can set the move generators if you want to make moves along certain directions or rotations, or you want to do swapping in the translations, you want to do stacking faults and voids. We didn't speak about how you can readjust the parameters of your constraints. We didn't speak about any of that. So I will stop here. That's a topic that we cannot abort in 1 hour. We need much more than that. Hopefully that was important enough to you. I will always be happy to answer your questions. Thank you very much.